video is the sound, but what's on the screen.
It shouldn't be.
When I looked at the video on YouTube, there wasn't any sound.
I think the first one you posted didn't have.
Oh, okay.
Yeah.
Oh, okay. I must have had my mic muted because it was like it's supposed to. Okay, then I had my mic muted. I apologize. This one I didn't record. I told you, keep track of the little dot. All right. It's the most important one's actually coming up at the end, so I think that's we're okay. All right, so you'll be able to figure out like if a die is fair because we're going to actually be able to look at the probabilities and compare it to what we got to determine if it's off by enough to make the dice not fair. Okay, those are the types of things we're going to be able to get into, which is kind of nice, kind of cool. All right, so this is the problem. Let's do this problem. Nope. All right, Charlene just put down payment on a lot in a small subdivision. There are 10 lots in the subdivision. They're all approximately 0.25 acres in size. 5 builders have been contacted by the subdivision manager to each build 2 homes in order to finish the subdivision in 6 months. Charlene's uncle is one of the builders contracted by the subdivision manager. What is the probability that Charlene's uncle will be the builder that built her house?
Yeah.
Sounds like a lot of them. Yeah.
Okay, so there's a ton of information in this problem, right? What do we care about? There's 10 lots. Okay, so we go 0, 1, 2.
So this is where we'll have a uniform.
Right, because there's no like we don't know like each lot's equally done. Like there's nothing in here telling me that well lot 1's going to go to this person, things like that. So we don't know. So each one's equal. So this is a uniform distribution. So 1/10, 1/10, actually 0.1. So 0.1, 0.1, 0.1, 0.1, 0.1.
There's only 5.
0.1. Right, but we have to look at the lots because Charlene's is only one of those lots.
Yeah.
Okay. So, and then the builders are, there's 5 builders, right? So they're each doing 2 of them, correct? So what's the odds of, I missed a 0.1 somewhere. Oh, I did put a 0, you're right. Okay. Yeah, that's fine. There we go. So what's the chances of Charlene's uncle building her house? 0.2. That's the answer. No, you could have done it and just said 0.2.
I'm not like the builders. You have just done the builders.
You could have done the builders, but since Charlene's house is only one of those, like you could have done it with the 5, but then you'd have to figure out like, okay, Charlene's house is one of those 5. You could have done 1 and 2, 3 and 4, like put it together like I just circled them at the end and put 0.2 underneath each one of them. That would have been fine too. The concept of this one was it's uniform. There's no like, we know they're going to do specific spots or whatever else, so the probabilities are going to be the same no matter what. Yep. Because each one's building 2. Yeah. Yeah. It still would have been.
But you got rid of the 10?
No, I actually got rid of the 0. I actually wrote 11 numbers up there because I did 0 through 10 instead of 1 through 10. The probability that there's 10 houses, each one is 1/10 of a probability of being built, and then since each builder is building 2 of them, there's a 1/5 chance that the builder would be building that house.
Oh, okay, because that house is one of. Oh, what is 0.1? Is it 10?
Yes. So her house is 1/10 of the place, but since their builders are building 2 of them, there's a 20% chance that her uncle would be building hers because it's one of those two that he would get. Yeah. All right. So here's the would you like a 5 or 10 minute break before I go into the last section, which would be the long section? Do people have to go to the bathroom or something? Like I have to go to the bathroom. All right, 5 minutes, go to the bathroom, get a drink of water. I'll be back. Or hang out for a few minutes.
Yeah, we don't want to go.
I know, it's fine, it's fine.
Yeah, I just did that there's.
Just be people. He'll be doing this my one part.
Oh, okay.
I'll just be doing that. Like no butter, so just.
Yeah, it starts beeping. As long as you are okay, that's all that really matters in the end.
You good, even if it dies.
That's the piece that matters. All right. What does binomial mean? There's two. So the main point in a binomial experiment, that's what we're going to look at now, is that there's only two outcomes on each trial. Okay? They don't have to be like heads, tails. It could be, but it doesn't have to be true, false. It could be agree, disagree, like those type of things. So there's only two possible outcomes. There's not strongly agree, neutral, disagree, strongly disagree. That's not binomial. Okay, it's agree, disagree. The experiment consists of identical trials, so n identical trials. So you would do the same thing to a group of people or whatever you're looking at. Okay, but they have to be asked the exact same question and come up with, like, have the exact same options. The probability of success, depending on which way you want to look at it, is denoted by P, and the failure is the opposite of that. So it'd be one. So in this case, we could use the why can't I think of the word? The opposite, but it's not opposite. I can't think of the word now. So would be 1 minus P. They also look at it as Q sometimes. So if you see Q, that is also the same thing as saying 1 minus P. It'll come to me in a minute. All the trials are independent, which means they have no impact on each other. Okay? And the binomial random variable is the count of the number of successes in the trial. So if we're looking at agree and disagree, you would say agree would be the successes and disagree would be the failures. So you would count the number of successes. So that would be the agree ones. Yes, that's what I was trying to think of.
I knew it started with a C.
I'm like, why can't I think of the word? Yeah, it's the complement because it's the exact opposite of it. 27. Yeah, it'd be the exact. It'd be 1 minus that.
Or I mean, 0.7.
Yeah, I know what you meant. So if the percent is 73% was the success for P, the complement of it or the failure would be 27% because it's 1 minus that. So it's the complement. It's the exact opposite. They have to add up to 1 or 100 depending on if you're using percent or. Yes. Yep. No, they do not have to be equal. Yeah, that's actually a very important thing. The experiment, the probability does not have to be equal of the two. It's just there has to be 2 options. Okay. If it was equal, this would be a really easy lesson. But yeah, a binomial experiment doesn't have to be equal. It just has to be 2 possible outcomes. All right.
And when you get to the random variable, the opposite is the complement of that would be the number of failures.
Yeah. All right. This is the formula for it. And depending on, I'm actually going to show you, because depending on how you're going to use this, sometimes it's actually easier to use the formula than to use their calculator for it. Because you're just changing a couple numbers, but I guess it doesn't really make much of a difference. Let's see. Actually, there's because it's a quick change too. Oh, that's not what I want. Yeah, it's not that hard on theirs either, so we'll just use theirs. So basically, if you notice the way the formula is set up, I'm going to explain it to you so in case you see it. It's kind of interesting. Remember NPR and NCR we talked about last class? So this is CR because order doesn't really matter because the trials, it doesn't make a difference which order you're picking them in. You're really just thinking about successes in that case. So that first part is how many values out of them you're going to choose. So how many successes do you want? All right. And then P is your probability of success. And then 1 minus P is the opposite of that. So if I have 100 people and I want 60 successes, I'd have 40 failures. So it'd be 6, the X would be 60 and the N minus X would be 40. It's the opposite. It's not the end of the world. As we're going to use a calculator to do it anyway. But that's the formula. All right. So let's actually do it. So rolling a single 6-sided die 4 times, and we're going to record the number of 6s observed. So the first question is, does the number of 6s rolled in the 4 tosses of the die meet the criteria for the requirement for a binomial random variable? So the criteria was that there's only 2 outcomes, right? So is there only two outcomes in this case?
Well, unless the outcome is like
Closest
either.
six or not.
Yeah.
Right.
I guess it could be, yeah.
Okay, so that's why I asked that question. So, because the question isn't what's the number that's coming up on the die?
Is it six or?
Is it a 6 or is it not? That's the question. Okay. So, yes, it fits that piece. Second part of it was, does the experiment consist of a number of identical trials? Yeah, how many trials am I doing in this case? I'm doing 4 trials. All right. The probability of success on any one trial is denoted as P. What is the probability of success? One-sixth. Okay, so I have 4 trials, and my probability of success is 1/6 or 0.167. Does the probability stay the same from trial to trial? Yeah, the dice isn't going to change, and it's not. And rolling the die once doesn't change the fact the next time I'm going to roll the die. Right?
The P, the 1/6, is that because it's the six-sided die?
Yes. Yeah. And because every side has an equal chance of coming out. So if it was a 20-sided die, it would be 1/20th. Because it'd be 20 cents. All right. Does that make sense? Okay. So now, X is the number of times we can come up with our, how many times the 6 comes up. So we have 0, 1, 2, 3, and 4. And we want to know the probability of X. Okay.
Wait, why is there a 0?
Because we could have no 6s.
Oh, there's a number.
Yeah, we're counting the number of 6s. So you could possibly have no 6s that would come up in those 4 rolls. That is a possibility. Okay. All right. So we're going to use this calculator. So it's called the binomial distribution calculator on the same website. First thing I want you to put in is what's your P. So in this case, it's 0.167. The next thing it wants us to do is the number of trials. So in this case, how many trials did we do? 4. The number of successes is going to change because we have to do this 5 times. We have to do it for 0, 1, 2, 3, and 4. So let's do 0 first. That means I have no 6s that came out when I rolled the die 4 times. I got no 6s. So to get no 6s, probability is 0.4814. So 0.481, we'll do it 3 decimal places. Okay, so that would be for X's no 6s. Okay?
What did you put the number of successes?
0, because there's no 6s.
There is using K for that. Since Q.
No, Q was the opposite of P.
Oh.
So if you see Q, that's the opposite of P, which you'll see sometimes. And actually, I think in one of the later formulas, you're going to actually see that. All right, so the next one we have to figure out is 1.
0.386.
Yep, so 0.386. and then 2. Five, 1, 6. And then 3 and 4. Good. Yeah. All right. That's our probability distribution. So if you remember the past couple that we've done, we did the uniform one where they were all the exact same. And the one we did before that, we either had a frequency table that we came up with it, or it was given to us, what the probability of each of those were. If it's a binomial distribution or experiment like we did here, there's only 2 possible outcomes. And we know what the probability of one of those outcomes would be, we can determine our probability distribution using that formula and calculate. Okay, so it gives us the probability of those occurrences happen. Okay. Does that make sense? So all that calculator did was plug the numbers into that formula for you. So you don't have to actually do it. So what's the chances of getting more than 2 6s? Correct, because we're just adding the 3 and the 4. Okay. Do you have a better chance of getting no 6s or at least 1 6?
Or
The 2 that I just asked you, are they complements of each other? No 6s or at least 1 6? They're complements, right? Because no 6s would be 0, and at least 1 would be 1, 2, 3, and 4. So is 0 more than half?
what?
It's less than half. So therefore, 1, 2, 3, and 4 would have to be more than half. So you have a better chance of getting at least 1 6 than no 6s on those 4 rules. It's close, but you do have a chance. All right. What did I do next? All right. According to a recent national poll, this book was written like 6 years ago, so not that recent. Actually, I think it was written almost 10 years ago now. According to a recent poll, about 40% of Americans believe in ghosts. Assuming this percentage is accurate, if 20 people were randomly selected and asked if they believe in ghosts, what is the probability that 12 or more would say they do? So what do we need? What's my P? 40%. So the probability is going to be whatever they're making the assumption that that's what they've done. They've done studies on it. This is the number they've come up with. What is my N? How many trials did I do? I asked 20 people. And what is my number of successes that I want? I want 12 or more. So I want K to be greater than or equal to 12, right? Okay. So we go back over here. We plug the numbers in. 0.40, 20 trials, 12 successes. And the nice thing is, if you look down here, you then have to pick which one it is, the correct less than or greater than symbols that you want. So we want it greater than or equal to 12, so it's 0.0563. Seven, 11, 12, 13, 14, 15, 16. Okay, that makes sense? So with this, we can start using data that we have and pulling information that we have to start determining what would happen in a smaller group of people. Okay. These you're not going to use a calculator for because they actually are really easy to do without a calculator. I mean, you can use a calculator, but you're going to use a regular calculator. So same concept we did before. You have your expected value and your variance and your standard deviation. The expected value, oh, actually they didn't use Q, which is good, is it's the same thing we were looking before. It's your mean. It is just N times P. Okay? It's whatever your trials is times whatever the probability is. So in the last problem, we had my P was 0.40 and my N was 20. So my mean is just 20 times 0.40. Which is 8. Your standard deviation is NP and then 1 minus P, which is the opposite. So in this problem, it would be 20 times 0.40 times 0.60. Where did the 0.60 come from? It's just the complement of the 0.40. Okay? These two have to add up to 1. It's the opposite number. If you're using the regular calculator, if you go sideways, you'll get the square root symbol. Actually, the square root symbol is on the other one too. For this one, you get 2.19. So again, as with everything else, those are just giving me information about how things are spread and what I would expect to happen. And if you think about it, this is just going to be whatever the probability is times that. So if I have 20 people, if 40% of them believed, I would expect 8 people. That's what that means. Okay. If it was 50%, I'd expect 10 people.
So when you got the 60, you said it was from the 40 and the 20?
No, it's the opposite of the 40. It's the complement of the 40. Remember, it's the exact opposite of it. So if 40% believe in ghosts, 60% would not believe in ghosts. That's where that other number comes from. Has nothing to do with the 20. It's the complement of the 40. So it's 1 minus P. So it's 1 minus 0.40, which is 0.60. All right. I think. Few problems. Anybody drive up Route 2 recently, or not even recently? See the purple lights?
I hate that at night.
I actually like the purple lights better than the white ones.
Yeah, I know that.
So the state bought light bulbs, and the purple ones are actually defective. But it's only worse when it's raining. When it's not raining, it's actually nice. Like it's a nice light. It's not blinding you or anything else like that. But they were defective, so now the state has to pay more money to get more lights to actually put them up. It's a whole nightmare. It's going to cost us more money. It's basically what the end result of it is.
Something random up order originally. The same thing happened down there.
Yeah.
I went back home to visit, I noticed it.
Yeah.
I saw it here. Ironically, it's actually the same company.
Oh yeah, it is. It's the exact same company. So the only reason I thought it was because this problem's about traffic lights. It's like, hey, light bulbs. So a company that makes traffic signal lights buys switches from a supplier. Out of each shipment of 1,000 switches, the company will take a random sample of 10 switches. Can they look at every 1,000 switches and test every single one of them? They could, but it's going to cost a lot of money and time and effort, right? So the company will take a random sample of 10 and access the number of defective switches. So the question is this a binomial experiment?
Yeah.
What's the success is?
The word of third doesn't.
Right. So in this case, the success is actually it's a defective switch. Okay. Company has a policy of rejecting a lot if they find any defective switches in the sample. What is the probability that a shipment will be accepted if, in fact, 2% of the switches are actually defective? Okay. I'm going to shrink this a little bit so we can write next to it.
So 2% for the effective probability that 10 of them have, but there will be at least one defective one.
Correct. Yes. So in this, so we're going to look at, so my N is what? Or actually, we'll have two things. So N is 10. P is 0.02. Not 0.2. 0.02. Again, really easy mistake to make. And what I'm looking for is if any of them are defective, right? So do I want to look for greater than or equal to 1? So I'm technically looking for greater than or equal to 1, right? Because that would be the number I want, right? When we're looking at doing a bunch of calculations, if I did greater than or equal to 1, I'd have to do 1, 2, 3, 4, 5, all those other ones, right? Yes, the calculator that we're using is going to make your life a little bit easier in that respect. But what would be the easier way for us to do this? Find 0 and just subtract from 1. Because that's the exact opposite of it, right? So especially if you have a lot of numbers and everything else that you're looking at, sometimes it's easier to go the opposite direction. So in this case, I probably would be looking for just x equals 0, and then I would just take that number away from 1 to figure out if I would reject the sample. All right, so let's go to the calculator. So my probability is 0.02. I'm doing 10 trials, and I want no successes. Yep. So this equals 0.817. So I wanted the opposite of that, right? So I'm going to do 1 minus 0.817, which gives me 183. So that would be the probability that I would reject the shipment. Yes, that's the complement of it. Yeah. Because I did equal 0. Instead of doing the equals 1, equals 2, and adding them all up, I did equal 0. The calculator that we're using, if you put 1, remember it has that option in there. So if you did 1 and hit calculate. So it actually gives you that number as well. Yeah, and it was,
But that's not less than an equal to, that's just less, greater.
Because we want more, there's at least one.
it was at least 1.
defective, So you want to look for more than one.
Right.
Well, wouldn't we look for the, you know how you look on here for the
Yep.
greater than or less than, why wouldn't we use that?
You can. You absolutely can. You could. Depending on the calculator you're using, not everyone's going to have that option. That we're using that one. So this one gives you all those options. So actually, if you did 0, you could say greater than 0 would have given you should have given you the exact same number, right? Yeah, if you did greater than 0, it gave you the exact same number. Because greater than 0 is the exact same thing as saying greater than or equal to 1. Because remember, these are discrete, right? That's a very important piece. When we start off the class saying we're talking about discretes today. There is no number between 0 and 1 in a discrete system. If it was continuous, there would be, and that would be 2 different values. So, but in this case, since it's discrete, those two mean the exact same thing. And yes, it would give it to me without having to do the complement of it because of the calculator we're using. So we would reject, no matter how you calculated it, we would reject 0.18. So about 18% of the shipments would be rejected. What happens if it was 5% were defective? Now we're rejecting, how much are we rejecting if it was 5%? Yeah, 40% of the shipments. So if there was a 5% defective rate in the shipment, we were rejecting 40% of our shipments by just randomly picking 10 light switches. So the company goes, wait, we can't reject 40% of our shipments. That would be very, very bad. So, well, we'll accept 1 defective switch in our pile. So now we're looking at no more than 1 defective switch. So we want greater than or equal to what? 2, or greater than what, right? And since I already did the greater than 1.
1 at that point.
Yeah. And the 5% one, it's 5%.
I mean, they'd only reject 40% if it was 5% every shipment they get.
Right, but so they don't know, based on their internal data, they know that 5% of their switches are defective.
But in every shipment.
No, in general, they know that 5% of their shipments are defective. So they're coming out of the factory. They know this is true. So out of every 1,000 shipments, we don't know what's in there. They're going to randomly take 10 to test it. If they take 10 out and they're saying that they're going to reject it if they find any defective switches in those 10, they would reject 40% of their shipments at that point. However, if we go up to say, well, we'll accept one bad one, at 5%, now we're only rejecting 8% of the shipments. At 2%, we're rejecting just over 1% of the shipments. That's the 2%. So the companies go, yeah, that's more acceptable. Because remember, they're only picking out 10 out of 1,000. So, and believe it or not, this is how we check everything. So when food comes into this country, they don't check every single container of food. They pick a random box and they check the box. And as long as that box was good, the whole shipment's approved. Okay? Anything they do. If food's coming off the line, when they go into inspect plants, when food's coming off the line, they're randomly picking a few things and they're going to test that for contaminants. If it's contaminated, they reject the whole lot. They make them shut down, clean the thing, and do everything else. But if it all is clean, everything goes through. The next one next to the one they picked could have been contaminated, but doesn't matter because they can't check every single one of them. Okay. Everything works this way. How many people have ever been bumped off of an airplane? Good. I almost did. I was coming back from a trip and that was in Charlotte, and they were asking for people who'd be volunteering to jump off the plane. And I'm like, sure, gonna give me a hotel, and I was like, absolutely, no problem. It's like I'll extend my vacation. But it happens, and a lot of times they'll overbook the planes on purpose because they know not everybody shows up. There is a certain percentage of people who do not show up to their flight. Okay. And they want their flights as full as possible because that's how they make money. So this small commuter airline, because obviously if we did a full jet, this would be a lot more difficult for us to calculate, is concerned about reservation no-shows. They assume that their commuter planes will hold 15 people. So these are a little small. Industry research indicates that 20% of the people making a reservation will not show up for their flight. All right. On these type of planes, a lot of our business people and stuff like that, like, oh, their meeting got canceled and stuff like that. It's like they don't really care because the businesses are paying for it, so it's the business expense. So yeah, they're looking at 20% will not show up for the reservation. All right. So the question is, first, is this a binomial experiment? Right, because the option is show up or don't show up. Those are the options. All right. So, first, if the airline decides to book 18 people for the flight, how often will one person not get a seat? So, we need three things, right? We need P, we need N, and we need K. So P is what? Okay. What's the N in this case? Well, we're booking 18, so there's 18 tickets sold, right? So there's 18 tickets sold. And then that would be 15, but that's the number of Right. So the question we have to look at is what is a success? Is it a success they show up or they don't show up?
Yes, they don't.
The question was if they sold 18 tickets. So this is they don't show up, correct? Okay. So we could make the success they show up, and that number would be what? 0.8. Okay. You could do it either way. That doesn't make a difference. You could do it either direction. But we'll leave it the way they have it written. So that's the success is they don't show up. So how many people do I not want to show up for this flight? I want 3. So if 3 people don't show up, then everybody gets a seat, correct?
Yeah.
We want that somebody's not going to get a seat, right? Right. So we want when X is less than the 3, right? We want the less than 3. Because that would mean somebody would miss the flight.
That would be either the 18 or the.
Yeah, it'd be 18 people or 17 people or 16 people showing up. Yeah. So less than 3 would be right. So if they sold 18 tickets, 27% of their flights, somebody would not have a seat. Okay. What if we did 17 people? So P is still the 0.20. N is still 17 now. What's going to be my K now? Be 2. And we still at less than 2, right?
That's because if any more than 2 miss, then the flight's not full, right?
Right. But we're asking if somebody's going to get bumped off the flight. So we have 15 seats, right? As long as less than 2 people don't show, if less than 2 people don't show up, or actually, yeah, 2 or less, yeah. Right? Should that have been X is equal, less than or equal to 3? Oh, it should have been less than or equal to 3, you're right. It shouldn't have been less than 3. It should have been less than or equal to 3. Hold on, I gotta change that number. Because, yeah, because it'd been 3, 2, 1, or no, nobody, yeah. So this one actually is that way. So hold on. So yeah, at 18 people, half the flights would actually have somebody miss the flight, which would not be good. Okay, so now we go to do the 2. And now we're at 0.3, right? Yep.
Can you explain why it's 43?
So how many seats do I have? No, we have 15 seats. Right. So if 16 people show up, 17 people show up, or 18 people show up, somebody's missing a seat. That's 3. As long as I have 3 people not make it, everybody will be good. So, but it's equal to 3 because if 3 people show up, my plane's still full.
But if there's two.
No, wait, hold on. I was actually right the first time. Because if 3 people don't show up,
Yeah.
everyone would get the seat. So I was right the first time. Yes, it was less than 3.
So you show up. Only 2.
There you go.
show up.
I was right the first time. Wonderful English. All right. Yeah. Yes. Yeah, because if there's 17 people, if 2 don't show up, we're good. If one shows up, or if none show up, then we're bad. So it's less than 2. Yes. So 11% of the time we'd have somebody that wouldn't be able to make the flight. What if we did 16 people?
So, yeah, in case you would. Oh, it's
Yes.
like 3%.
Yeah.
In the end, you just make it up, correct?
No, well, the end was the question. I'm reading the questions from the book. You're just not seeing the questions. You're hearing me ask the questions.
I think you're asking which side where one of the people of the
Okay.
sides go, right?
Right.
If 2 people don't make it, one person still gets dropped out, right?
So in the very first example, when there was 18 tickets sold, if 2 people don't make the flight, or if
Oh, but the flight's still full, so they.
Right, we're good. yes. Right, that's the thing. It's if all 3 people show up, if all 18 people show up, the flight's full. If 17 people show up, the flight's full. So it's if nobody doesn't, because remember, we're looking at the opposite of it. So if nobody doesn't show up, I mean, if everybody shows up, so that means nobody doesn't show up, which is the opposite. That's what we're looking at. That's 0. And then it's 1 person doesn't show up. If 2 people don't show up, we're good. That's the way it works. Because it's the opposite.
People that don't show up.
Right.
Right.
Okay. You could, that's the way the question was worded. So that's the way we're doing it. You could have easily gone the other direction and said, use P as 0.8. And said, okay, 15, the flight's full. So if it's greater than 15, then we have people that are missing the flight. You could have easily done it the opposite direction at that point and just used the 0.8 instead of the 0.2.
Then you get how many people don't.
Well, then you get how many people. No, then since we're still going to calculate what the flight, because we're just looking at the other direction. It's just the way you're thinking about it is different.
It would be 80 people, 80% of the time people show up.
Right.
If you sell 18 tickets, 3 people, that percentage would then be,
Yes.
yes,
Yes.
okay.
Okay. All right. So this is the bad side, right? This would be this is the customer service nightmare, right? Because these are people, this is a situation where people are going to be there expecting to get on their plane and being told, sorry, we sold you a ticket that we didn't have room for. Okay. What's the other direction? There is a situation where there's empty seats in the plane. Okay. So if we look at the same thing, but this time we want actual seats, like leftover, like empty seats on the plane. So when are there's going to be there? How many times is there going to be at least one seat empty on the plane? So let's actually do this the other direction since it makes a little more sense for us. Let's do the 80. So if I sold n equals 18, I want less than 15 seats on the plane, right? Yes? That would be at least one seat empty. So I want less than 15 people.
But less than 15 for all.
Yeah, because I want to know if I sold 18 tickets, how many times I got to fly with less than a full plane.
Yeah.
So that means I want less than 15 people on the plane. Because in terms of me making money, I want a full plane. So if I sold 18 tickets, half the time my flight would be full. If I sold 17 tickets, almost 70% of the time my flight would be full. If I sold 16 tickets, 86% of the time my flight would be full. So which policy should I make?
No. Eight. Because it's smaller. Better, right?
Overall, you got both directions, right? And if you were the airline, which decision would you make? Selling the 16 tickets?
Yeah. I would say. Oh, it's smaller. Well,
I don't know, I'd probably split the difference and do 17.
yeah, but.
So, but that's the thing. It's like you got to think about it. It's like, and in all honesty, it really depends on how much they would have to pay each person that's not getting on that flight. So, how much of a hassle is that really worth? Like, so that's what I said. I'd probably split the difference. I'd probably do 17. But these are decisions that, looking at these type of numbers, you would need some more information to make those decisions based on it. But these are the situations, these are the numbers that they would look at to make those determinations. Okay. All right. One more problem. I'll give you guys a choice. So here's your 6 options. These are all real studies. This is a real study that I'm going to pull up. And we're going to do it based on this classroom. Which study do you want to look at? everything would be a hot button issue no matter what you're going to look at. And that's the thing about research studies. Like they're not looking at stuff that everybody agrees on. They're looking at stuff that's controversial. So pick one. Huh? Law and criminal justice? All right. So this is the study on law, the first study on law and criminal justice. That's the study. That's the law one.
Yeah, I agree.
Well,
Because it's law. So hold on. I'll get the question. There's a bunch of questions. This is the one question that's specifically about law. All right. First off, is this a binomial experiment? No, because there is 5 options. Okay, we're going to make it a binomial experiment. Okay. Oh no, it's quite easy because it's strongly agree, neutral, disagree, and right. So we're going to make, since we're talking about should it be, we're going to take those two, and that's going to be my
Oh,
positive
okay.
agree. So what's that, 40%?
Yeah, 40.
And we're going to pick all Americans because we're not, the other ones are different levels of Christian, like how much they believe in Christianity. So like this is very, like they're very Christian. So obviously that's why every one of them, yeah. Sympathizers are ones who go often or would consider themselves Christian, but not like diehard Christians. Skeptics would be the other ones, the opposite direction. Like people who are necessarily religious, but not maybe necessarily Christian. And then the rejectors are the ones who aren't Christian at all, who could care less about Christianity. So
that would put forward religions that aren't.
or atheists and stuff like that in those situations. So, but even people who are like necessarily somewhat religious, like even if they're another type of religion, some of them also believe that like there should be some basis in, because people look at morality as the religion more than not religious. And that's where this piece comes into play. All right, so we said 40%. Okay. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of you in this classroom. Okay. So my P is 40%. So 0.4. My N is 16. So so my K is going to be 8. So I want to know.
Did you just make up the 16?
No, that's exactly how many people are in this classroom.
Oh,
I want to know what's the probability that more than half of you agree that the U.S. law should be based on Christian values?
I just think it's gonna be a more strong.
More than half would be greater than 8. Figure it out. Find the calculator. That's what we just did.
you wanted to know what was it again?
I want to know more than half, or at least half. I'll say because I want 8 or more. So my K is 8, and I want X is greater than or equal to 8. So based on my question, there's a 28% chance that half of you believe this is true.
Say more than half.
Yeah, so I wrote it as greater than or equal to 8 or more. So,
But I mean, in reality, that won't be true. It's not like a perfect.
no, that doesn't matter. So this is the thing when you're looking at, notice how nowhere in it did it say it had to be a random sample. So once you start looking at the data for a nation, when you get the information for the whole nation, they use that to then look at any groups of people to make those decisions. And in all honesty, this is a pretty random sample. Like there's no like they
We're all
hand
one
choose
area.
you. Yeah, right. You're in one area of the country, but it's not necessarily you weren't picked to be here. So you can think of that as somewhat of a random sample in that respect. So, but knowing nothing, and that's the thing, was like when you know nothing about it, you look at general trends. And there's a lot of things that make these or what politicians and people make decisions based on. Okay. If you're looking at the country as a whole, if you can get 40% of the actual voting population to vote for you, you won an election. Because 100% don't vote. Okay. So if you can get 40% of the entire country, you won. Okay. So when you're looking for making those decisions, this is what people look at.
But then also, I mean, this like they calculate these data. They couldn't have asked everyone.
No, they never have to. This one actually, I can give you exactly how many people they asked because it told me in the study. Hold on. This study, they asked, come on, give me the actual numbers. Of course, this one they didn't ask at the beginning. They didn't tell me that at the beginning. They surveyed more than 6,000 people, which is significant. Actually, we're going to do it. We're going to actually do the calculations, and it's somewhere around like 3,000 people is all you really need in the United States to make a decision.
But I mean, it matters like where you get.
Well, this is everywhere. They do it. They did a random sampling across the entire country. So of 6,000 people. So yes, if they did just the Northeast, they might get a different response than just the South, like the Bible Belt area. They would get a different thing. But when you're looking at the whole country, those are the types of things that they're looking at. So it's like, I'm not saying you are that or anything else. It's just, this is one of the things that comes up. Want to do one more? Pick another one.
Religion.
Keep going on the religion.
Let's do immigration. So this was the study. And they asked, let's see. Sometimes it's hard for me to actually find the exact number of people they asked, because some of them put it at the beginning, some of them don't. And this one doesn't tell me how many they asked. I'd have to keep searching it. I don't feel like wasting a ton of time searching for it. All right, let's see. Which question do I want to show you? All right. So this was part of the study. This was some more of the information they got.
Oh, crap.
No, there's no graph for this one. So nearly 6 in 10 Americans, 57%, say immigrants living in the United States illegally should be given a way to become citizens, provided they meet some certain requirements. More than 1 in 10 say they prefer the undocumented immigrants be eligible for permanent residency status, but not citizenship. All right, so we'll take the 6 and 10. So your P is 0.57. Your N is still 16 because that's how many of you are in this classroom. Just because I feel like being controversial, let's do the opposite. We'll do less than 8. Believe this to be true. So there's a 21% chance that less than half of you believe that. So it's the chances are that the majority of you believe that to be true. Okay. But that's what I'm saying. That's why it's important, like, and we're going to get into a lot more of these type of statistics and stuff like that and how these studies and stuff are done. But that's why I said at the beginning of class, like, I think statistics is one of those ones that it's becoming more and more important to understand so that you can look at these studies and understand what's going on in them. One of the actual studies that I looked at before, and I can't remember, I think it was the politics one. Oh, wait, or maybe it was race. So maybe it was race. They asked, so they asked the questions in different ways. Oh man. And now I can't find the study again. So when they're asking questions, they'll ask them in 2 different ways, the same question. So this way, they can see if you really are listening to what the question says. Because the goal is that one question when you would answer one direction, the other question you should answer the exact opposite direction. Okay. So if you're doing it, if that's what you actually mean. And they do that to start to weed out those people that always pick agree or always pick disagree, things like that. Because they want to weed those answers out because those aren't people who are actually taking the survey seriously. So they do those things to be able to filter out that bad information. Okay. Or there's biases known on where they put the people. So if you're being asked who you're going to vote for president and you list the people in order and the same order every time, the first person or the last person will always be picked more than the people in the middle. Because you key on the words, like you're listening only to get the answers and you're going to pick whatever the first one is, or you're not totally paying attention and when they get to the last one, oh, that's the one I want. So it's like they have to filter these things out. So, but these studies have an impact on us. Okay? They make decisions based on that stuff. So, and as you can see, some things are bad, depending on your viewpoints, they could be a bad direction or a good direction. It's like, it's a matter of which direction you think you should be going with. So, but yeah, that's my goal, and that's what we're going to get to towards the end. We'll start looking at how the studies are actually done and the hypothesis testing and those type of things. So, all right, we are done for the night. We will do chapter 8 on Monday.